So I'm going to talk about TBA, which is a super cool new concept. It is taco-based acceleration, and it's the new thing. It's like TBA.js, probably not registered on GitHub, and it is. Damn it. Okay. Anyway, never mind. So we're not going to talk about TBA today. We're actually going to talk about, as Jessica has already spoiled, and is probably also on the website, I think. I'm going to talk about JavaScript in parallel. Now, you might have heard that JavaScript is single-threaded and has one event loop, and that we do not really have a concept like other languages do, like threads or coroutines or something like that. But let's have a look at how we can deal with this nonetheless. So this talk basically introduces us to a problem, the problem of edge detection. I'm going to explain that in a second. Then we're going to have a look at how we can solve that with normal JavaScript. But then we're going to look into something that's called web workers. It has been around forever, basically, but people are not using it as much, I think. And it's definitely worth having a look as to why we should use them and what they're good for. And then actually I'm going to dive into something that is normally used for graphics, specifically 2D and 3D graphics in the browser. We're going to look into using the GPU, the graphics processing unit, to do heavy workloads in the browser without having to resend to a backend. All right, so first things first, edge detection. Can you spot edge in here? Dim, 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 it's there. So, okay. Oh, the clicker died. Oh no, the clicker did not die. All right. So yeah, obviously I do not mean that edge detection. I actually mean something slightly different. What I want is, I want to take any picture and process it in a way that I find out where in the picture there are edges. So basically, gradients between two different colors. And so basically, the result I'm looking for, in this case here, would be something like this, right? So whenever there's an edge, so for instance, here there's an object clearly marked, or here's an object that is quite popular, or here's another object, I want to have a white pixel at its corners. Now this is a little tricky because there's lots of small light bulbs, so there's lots of corners or edges, and I want to basically filter the image for anything that is an edge, which is the very first step for computer vision, oftentimes, especially when you want to do object recognition or pattern recognition. You want to find the edges of objects. Now this is a technically not so hard problem, but it's still a bunch of calculations that we have to run. So basically what we can do is we can apply the Sobel operator on each of the pixels on the image. The Sobel operator basically looks and weights the neighboring pixels' colors and finds out if they are in a certain ratio to each other. And then we can find out if there is an edge or not. Oops, where's the matrix? We're going to see that in a second. So a lot of people, when they see the Sobel operator or the entire math that is behind it, they're like, what? And I particularly do not like math notation that much. I prefer to see it in a different way. So the very first step is looking at an image. We don't have to deal with color that much. What we are caring about most is brightness, or average between the different color values. So we have normally RGB, so we have 3 values that we have to deal with. How about we just add them and take the average, so that we get grayscale. And then we have values between 0.0, which means black, and 1.0, which means white. And then everything in between is a grayscale value on this scale. We could also use values between 0 and 255. It doesn't matter that much, because if we divide them by 255, we get on a scale like this. It's just easier for us to do the math with. So now if we want to see where is an edge in an image, we can do it like this. So here we have clearly an edge here, right in the middle of these pixels, right? So if we want to find out if this pixel is at an edge of this image, or if there's an object ending and another object starting, then we basically look at all the neighbors. Not at all the neighbors, though. In this case, we only want to find vertical edges, because we have a vertical edge here. The same principle applies to horizontal edges, though. It's just then flipped. Okay, so we want to find out if there's a vertical edge. So what we do is we look at 6 of the neighboring pixels. and we value them slightly differently. We weigh them slightly differently. So on the left-hand side, all the weights are negative, and the middle one is a little higher because we are looking at this particular pixel in the middle and not the pixel above or below right now. And then we do the same thing with positive weights on the right-hand side. So if we do this, we find out, okay, so there's like 0.5 on both sides of these, right? And so basically it's like -1, and -2. So that's like -4 times 0.5. That's, oh, come on. Correct. And now we do the same thing with positive values. What is it? 2, obviously. If the one thing is -2, the other thing is +2. And if we add these two values, if you do -2 plus 2, we get 0. All right, so this is a 0, which means the colors around it are very similar. So it's not really an edge. But what happens when we go to an edge pixel, though? Let's have a look. So we want to find out what this pixel is. Is this pixel an edge pixel, yes or no? We overlay our operator, and now we get different values. Now on the left-hand side, we still have the negative values. We still get -2. But on the other side, now this is all 1, because it's all white, right? 1 for white, 0.5 for this gray, or maybe even 0.25 or something like that. So now we have -2 plus 4. Oh, that's a different value now. Now we're looking at a value of 2. Huh. So if we do this for all the pixels individually without basically looking at the weights beforehand, we get this picture. And that's nice, because we clearly see that the values around the edge are much different from the values which are not on an edge. So this is how we can find out if there is an edge, or if a pixel is on an edge or bordering to an edge. We could make these larger or smaller, that's possible, but it turns out that this is actually normally a pretty good approach. If we want to do that thing for horizontal edges, what we can do is we can just like turn it, basically. And we do the same thing, just horizontally. And then we can combine these, and then we also actually figure out, hey, because of the weighting of the 2 in the middles, we actually even can spot diagonal edges. So that's kind of nice. Okay, so we have figured out how to do the edge detection. Great. How does that look like in JavaScript, though? So let's have a look. So first things first, I draw an image that I want to analyze onto a canvas so that I can get its pixel data out really easily. Hypothetically, I could also actually just like load a file using fetch, and then I have to decode it, which is a little tricky because it depends on what kind of image format it is. They're compressed and stuff. So I would have to deal with all that. With the canvas, I have the upside that I actually, A, get a visual feedback, and B, I don't have to decode it. The browser does the decoding work for me, which is nice. You could also use a service worker with a WebP decoder, but hey, let's not go too fancy. So we are drawing this image onto a canvas, and we are getting the pixel data out. And then we are calling a function that we have to write because it doesn't exist in the browser, highlight edges. And we give this the pixel data. We give this the color information for all the pixels in the image. And then later on, once this returns, it returns with a bunch of pixel data for the black and white pixels that represent edges or no edges. And then we just draw out the new pixel data onto the canvas, and then that's pretty much it. So how does the highlight edges then work? So we have to go through all the pixels, right? We want to find edges in all the pixels, potentially. So we have to loop through all of them. Okay. And then we have to get the grayscale value for each of these 6 pixels that we have to look at. And then we have to weight them as the Sobel operator does. So here you see the familiar -1, -2, -1, 1, 2, and 1 again. And these represent the pixels around the pixel that we try to figure out if it's an edge pixel or not. So let's, scrap that. We do that twice, actually. You could hypothetically optimize it a little bit to not have to look up the same pixels multiple times, but basically what we're doing here is we are looking at these values once, the values left and right to them, and then once above and below, so that we get horizontal edges and vertical edges. And then we take the square root of the sum of both of these values. So we have the horizontal edginess and we have the vertical edginess, which is a value that tells us the higher it is, the more likely it is to be an edge. We square them, we add them together, and then we get the square root from them. That's a way to get out a value that looks more or less something between 0 and 1 that tells you how edgy something might be. All right. And then if we find the edginess to be edgy enough, it's like, yeah, this looks like a good edge. 10 of 10 would edge again. So then we basically put out white pixels or a white pixel at this position. And if not, then we put out a black pixel for this position. But how much work is that actually? Or how much work is involved in doing that? Let's have a look at an image that is one screen. So basically a screenshot we want to find, or a movie frame or something like that. It's a full HD frame, so we have 1920 by 1080 pixels. Which in turn means that we have approximately 2 million pixels, a little more. And 2 million pixels means that, wait, what? 2 million pixels means that we have to look at all the other pixels around them, 6 of them for one go, for one Sobel operation. So now we have to look at actually 12 million pixels, and these pixels, one pixel is not 1 byte in memory, it's actually 3 byte because it's R, G, and B. Even though we later actually discard some of the information, we still have to at some point deal with all this information. So we are actually having a total of 37 million bytes approximately. Now, 37 million bytes or 37 megabytes does not mean much because that's basically a normal website these days. Or, yeah, I don't know, a screenshot thereof maybe. But let's put it in other terms. So I started doing computers quite a while ago, so for me that's like, what do you think? How many floppy disks? 3.5 regular fat formatted. Holy shit, no. Well, but I mean, impressive guess, great. 20 million, it's a bazillion because it's a child's number. Like, how many flies are there? Over 19, which is correct, right? There's definitely over 19. All right, so let's wind back. So if you've ever like installed, let's say, like Zack McCracken or Windows 3.1 from floppy disks, then this next number is going to be shocking enough. It's not going to be 25 million, but it's actually 25. So if someone said 25 over there, they're right. So, and if you have actually been installing like Windows 3.1 from floppy disks, then you know that was no fun. And I think there was like 12 disks or something, like 12 floppies. Alternatively, if you, like me, got on the internet on a dial-up modem with 56K, during night hours in Germany, when it was fast, for once, right, you would download 61 minutes on this. So we're talking one picture, one. Imagine trying to do that in real time with 60 frames per second. It's quite a bit of data that we are crunching here. All right, so having this written in JavaScript, we can put that into the browser. And actually, let's do that. And so that you don't have to do this, I have done this. And this is going to be fun because I have to type in URLs again. Yay. Jesus, no. There's the slash. Dash. All right, here we go. No, that's not correct. Damn it. Okay, the cool thing is, I blame Microsoft for this, yeah. Microsoft fixed this. Repositories, JS. Oh, I think it's actually high. Yeah, I jumbled the parts. Okay, fair enough. So let's run this on the main thread. So this is now downloading a picture. It's 2000 by 2000 pixels. It's the Frauenkirche in Dresden. I highly recommend, if you're ever in Eastern Germany, in Dresden, definitely check out the Frauenkirche. was burned down during World War II and has been reconstructed only like a couple of years back, so pretty nice. And here, but up here, and oh, I can't zoom like this. Okay, fine, then we just zoom like the lazy way. Not on this keyboard layout with keys, screw that. All right, so here we have this little like slider, and that's the threshold for the edginess. So this is relatively balanced, but let's drag this over here. Huh? Oh, that's strange. Oh no, what happened here? Can we drag it up a little like here? Ah, okay, so it does its thing, and it does make a difference. You see, like more is recognized as an edge. But it's not kind of nice, right? It's like I click, nothing happens. And the best thing is like, so let's click here, and now let's click here, and now let's click here. That took a while. That's not particularly great. Why does it take so long? Well, keep in mind, we have to process a bunch of data. And unfortunately, as I said, JavaScript is single-threaded. So we're doing this on the main thread. So if we look into the timeline, we see like, this is where the image is loaded and rendered initially, and there's like some renderings going on here. But if you see this red thing happening, this red bar on your timeline tooling, that's not a good sign. Okay, that means that we are definitely not running with 60 frames per second. And if you look at the frame rate, we're probably running at like 0 frames per second. So, slideshow basically. Not particularly nice. And if we look at where the action is going, or where the work is spent, then we have like a bunch of stuff going in here. Get image data, takes a little while, okay, fine. But then there's like this huge block of edge detection. And I'm using the user timing API here to actually get that measurement. So basically I can say when you enter the highlight edges function, and you come back later on, put that bar into my timeline tooling. And here we see that's a whopping 2.6 seconds there. So for 2.6 seconds, the browser is basically carrying out the work, which is figuring out which pixel to make black and white. But that means for 2.6 seconds, it cannot process anything else. It cannot respond to clicks. It cannot respond to resizes properly. It cannot flash anything. It cannot move anything. It cannot run any animation. So we are basically blocking the entire browser tab for 2.6 seconds. And if you've ever heard something about perceptual psychology, then you know that an immediate action is basically anything, I think it's between 0 and 10 milliseconds. We can easily connect the action that we took to what's happening as immediate, I think, until 100 milliseconds maximum. And then we start disconnecting. And I think it's like at 10 seconds, we are actually proactively starting to think of other things than the task that we are actually carrying out. So 2.6 seconds is definitely on the longer end of an interaction, and that shouldn't happen. That's pretty bad. But as I said, we don't have any threads or any way to like do it elsewhere, right? But that's not quite true. We have web workers for this purpose. Who here has used web workers themselves before? That's a few people. That's not enough people, probably. So web workers are a pretty cool concept where basically you can instruct the browser to load an additional JavaScript file, and then you can send messages between this worker, this JavaScript file that gets executed with its own event loop in the background, and you can send messages to and from your main document. So that's kind of nice. So you can offload the work, and you can run multiple web workers as well. So how does that work? Well, we take the same JavaScript code. We do not change the actual code. We just put it in a different file. You could hypothetically also do this with data URLs, but so many edge cases and interesting problems. But basically, here we are taking a separate file, and then we send the pixel data. So we got the pixel data still, but we send the pixel data over into the worker. And there's a quite fun trick here. This weird array syntax says, do not copy it. By copying, I mean, so the problem here is now we have two parts of JavaScript running at the same time, literally, not like asynchronous. No. Asynchronous just means like one thing runs at a time and an undefined or not so easy to guess time later on somewhere else on my same event loop. This is an actual individual event loop, so you cannot predict what comes first, really. So what normally happens when you leave out these square brackets is you get a copy of the entire pixel data into the worker that is independent of the original data. But we are not accessing the pixel data in the main thread anymore. We are not using it. We don't need it. So we say, all right, just push it over, and afterwards, in the main thread, this will be undefined, but in the worker, this will contain the actual pixels. This is called a transfer list. You can theoretically transfer multiple things. In this case, we are just transferring the entire array of pixel data over, so like lots of color values. And then eventually it is done with its work, and it comes back to us, and then we get the event detail, which is whatever payload you're putting into the message that you're sending back. In this case, the payload will be the new updated pixel data with the black and white pixels for edges and no edges. And that's it. Okay, that's not too much. And it looks slightly different. There's an interesting, like, you know, line dashed thing going on here. We can have a look at how that actually behaves in the browser. So I go back, and I run this in a separate worker. And now the worker has done this in the background. That's why we saw the original image for a second. And hey, look at that. It is still pretty smooth. I can still actually interact with it. It still takes 2.6 seconds to actually come back with the values, or in this case, might have crashed in the background. Who knows? This is not my computer. Oh, hi. DevTools looks slightly different. But there's nothing on the console which makes me hope for, no, it can't be bothered. Okay, cool. Ah, that's why I like live demos on someone else's computer. 21, 22, 23. You shouldn't take this long. What's going on this computer? Let's timeline this. Yeah, blah, blah, blah. You do you. Grab this over here. Okay, cool. Right. So this is running in a, why is this thing here? Just go away. So we are seeing that in the main thread, there isn't much work going on in this period here. But why is it not showing me the other threads? Here we go. Dedicated, no, where is it? Here, dedicated worker thread. So now there's like this additional dedicated worker thread that has a bit of setup in here, and then afterwards basically processes the message that it gets, which is the entire monster of the pixel data. I wonder what happens when I now do this again. Oh, now, okay, now it basically crashes. So that's promising. Ah! Of course, it's a Heisen bug, or no, it's a Schrödinger bug. Once you start observing it, it doesn't happen anymore. Clearly. So yeah, great. But here again, we see like this is the part where the worker takes over. And you can see the main thread isn't doing anything in this part of the time, whereas the worker actually does all the heavy lifting, which is nice. And the user timing tells us this is the time spent in edge detection, and there's like lots of edge detections going on with garbage collection. Okay, fine. You know, computer, just don't leave me for the third demo, please. That would be great. So here we see like the setup work stays the same, and the amount of time stays the same, but the browser tab remains responsive to what we are doing. So we have offloaded the work. We could even, basically, depending on what we are doing, we could even cut the time shorter. What we can say is, well, we could cut the image in smaller parts, and if there is enough cores on the machine, if it has like 4 CPUs, it can actually do 4 calculations at the same time. So if I cut the image by 4, 1 for each core, and start 4 workers, what I get, it would be basically a quarter of the time to actually do these calculations, which is kind of nice. It's a little hard to determine how much is a good value, though. I would argue anything between 4 and 8 probably is the same thing. If you are doing some network processing or file I/O or something, then you can even theoretically run more workers, because probably that's going to be the bottleneck. The network not coming back to you going to be the bottleneck. Here we are not relying on any network. Here we are just calculating, number crunching the entire time. So that's going to bind your CPUs. That's why this particular kind of workload actually highly depends on the amount of CPUs that you have available. Yeah, here we see that again. Nothing on the main thread. The actual work happens in the worker. There's a bunch of cool stuff that you can do with this. There's additional things that are coming out or being worked on. So there's the single instruction multiple data proposal, which allows JavaScript to use CPU extensions to actually run these massive parallel operations on different data, but as long as it's the same thing. Shared array buffer has recently been in the press because of the Spectre and Meltdown leaks, but we are hopefully bringing it back really soon, which is cool because then you don't have to like move data around at all anymore. You have one array buffer, and they share the data between the different workers, which is even nicer. We do not have canvas access yet, because hypothetically, even that part could have been outsourced to another thread, but because the canvas only lives on the main thread, so we only have access to its pixel data from the main thread, we can't shift or offload that yet. But it's being worked on, so we're probably going to get that. There's also shared workers. If you happen to have multiple tabs that happen to, do the same workload, you do not have to start a new worker. You can say this worker should actually be working for, if I happen to have two windows of my app or two tabs of my application open at the same time, they can use the same worker, so you don't have to spin up a new one. It's pretty cool. And then there's another thing. So sure, this is a computer graphics problem, technically speaking, but even if it wouldn't, even if it would just be the math behind it, if it was just be number crunching, you can use another processor for this. Inside your computers and phones are definitely two types of processors. One is the graphics processor, the GPU, and one is the central processing unit, the CPU. If you have lots of data and want to run the same or similar instructions on them in parallel, you definitely can probably leverage your GPU, because GPUs are great for putting a lot of data or crunching a lot of data at the same time. So let's do that here. It's a little messy, really. So like we have to read the pixel from the image and then like calculate where we want to read that pixel, and then, but this is still the Sobel operator, right? Like 1, 2, 1, 1, 2, 1. Here I just like do the minus and plus at the beginning of the line, but basically that's it. We do the same thing one more time for the vertical edges, and then we just have to see. This is the same thing. We do the square root of the squares of each of these edges. We have to access the data like this. And then here, this is where we do the grayscale transformation. If this is larger than the threshold, it's going to be a white pixel. If not, then it's going to be a black pixel. It's the same kind of thing. Jaume Sanchez wrote this original code, which is kind of nice, and he does lots of crazy, awesome great, awesome demos. No ableism is okay, ever. And this is what we get, and now I get a pretty direct feedback. Yay. The difference in timing is that JavaScript runs on the CPU, so can basically execute one instruction, so one pixel at a time. Whereas the GPU actually runs multiple pixels at the same time. Hence, we get more speed in here. And here we can see that. So this is the initial workload. This is basically like downloading the image and rendering it initially. And then afterwards, there's no work visible here. But if we look closer, then we see like in the main thread, there's a huge green block. Green block means this is actually not the main thread, this is actually the compositor. So this is the piece of the browser that actually talks to the GPU and gets data in and out to the GPU and from the GPU. And that's where the magic happens. And that happens in 827 milliseconds because I didn't optimize this code and it was a quite old laptop that I took this picture on. If you want to learn more about that, there's another example for this. There's Seth Samuel's talk from, I think the one I link is from JS Congress. He gave the talk multiple times where he shows what kind of workloads you can do and how to compare them or benchmark them against each other. And you can do things like floating point arithmetics really fast on the GPU rather than the CPU. You can do lots of matrix multiplications, and when you don't know what matrix multiplications are great for, it's cryptography, for instance. It is Bitcoin mining, I think not that much. Probably it is. I don't know. I don't do that much, really. But probably it is good for that one as well. All sorts of graphics problems and a bunch of other things can be really well formulated so that the GPU can pick them up. There's also a library encapsulating all the nitty-gritty details, so you don't have to write shader code and stuff. You can just write a bunch of JavaScript, and they basically figured out how to do that in the GPU. It's called TurboJazz. It's quite a fun project as well. And I'd now like to sum it up a little bit before we go for drinks and refreshments and enjoyment, probably. First things first, do not try or attempt to do heavy work on the main thread. Because browsers do not really tell you how much time they give you, but after a certain while, 2.6 seconds is probably fine, but people do not like it because A, it fries the battery, and B, if they're on mobile especially, and B, it basically blocks the browser tab, so it feels like the app has crashed, which is not great. Animations don't move, nothing works really, so do not do that. And as I said, if your work takes too long, let's say 10, 20, 30 seconds, the browser gives the user a pop-up that says, ooh, this page has become unresponsive, do you want to quit it? And the default is, yes, please take me out of here. So that's not really what you want to do. So get off the main thread, use workers or use something else like the GPU, but do not attempt to do heavy number crunching on the main thread. Also, WebGL can be used for more than just graphics because it is a great pipeline for parallel processing, as we can see here. It parallelly processes the Mona Lisa, which looks quite weird on this GIF, but it's fine. NVIDIA partnered with Mythbusters for this one, I think. And there is one interesting candidate that we don't know too much about yet in terms of how it will actually help us getting off the main thread much, because it's unclear, or it's clear how the interactions work, but it's unclear how you can basically use them properly. But we might see a lot of interesting work being done with WebAssembly in how the JavaScript main application can use WebAssembly in the background to do the number crunching. So definitely watch out for the WebAssembly talk tomorrow, as far as I'm aware, by Emil, if I remember correctly, who's probably here in the audience right now, or maybe not, who knows, it's sunshine outside, so I'm not a cop or a traffic sign, right, do whatever. So, get out of the main thread, use web workers, and the shared array buffers are coming back for round 2 after the security incidents, and use these transfer lists, as I explained, to not have memory duplication where you don't want it. WebGL can be used for all sorts of math. You do not have to necessarily do rendering with it. You can just express your data in pixel values and then basically push that into WebGL, which is kind of fun. And WebAssembly is very likely going to be a huge help here as well. So I like to wrap this up. The slides are online already. There is the demos online as well, and you can always find interesting stuff on my blog too. So this particular thing in much more detail has been described in one of the blog posts as well. And I would heavily be happy if you talk to me here in person today or tomorrow, and just chit-chat a little bit, or if you follow me on Twitter for more interesting things. Thank you so much.
All right.
All right, we've done it.
We're done. We can just hang out here, actually.
That's good.
For a while, yeah. All right, so one question I have from the audience is, what's the max number of web worker threads you can create?
That's a really good question. Moving on. I think you can. I don't know if there's any limitation really besides the fact that at some point your computer can't execute more. Probably there is a maximum. I guess they have an internal ID, which is probably 16-bit long or something, because no one anticipated 5,000 million web workers to run. But I wouldn't know right now at this point. But I guess the real answer to that question is it depends on your workload. As I said, let's say you have 4 CPU cores in your browser, and you do this kind of work, and you spawn 8 threads, then the first 4 will be like taking up all the computing resources you've got in your computer. So the other 4 basically have to wait for them to become available. So it doesn't really buy you much anymore. So the cost of dealing with so many workers and reconciling all the different results that come back basically eats up all the potential increase in speed that you might get from it.
Yeah. Okay.
Yeah.
Awesome. I have also been asked to ask you about chickens.
Jesus Christ, who did that? I have a suspicion it comes from over there, but all right. So
We're going to end on a light note. I can't say because I don't know where this is going.
So the thing is, that I have a talk that just uses the word chicken, and it goes on for like 5 minutes. I wonder if I can find the slides. But basically, so there's a beautiful research paper. It's literally written in the style of a research paper, and it's called Chicken, 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 and the subtitle is Chicken, 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 Chicken. And it has like all the diagrams and sources and quotations and tables and stuff, and I thought we need a tech talk that basically does exactly that, just like abstracts away all the content from the presentation and it's just a presentation. So it goes, basically the talk is called Chicken, 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 and it uses like custom elements and stuff, and it's pretty fun. It's like, if you want to write cascading chicken sheets, then let me know.
Where can people find that?
It's actually, I think it's on YouTube, or is it on Vimeo? I don't remember. But if you search for like Frontiers with double E instead of IE, Frontiers Chicken Talk, you probably find it. Oh, there's also github.com/chicken-chicken/chicken. It has an open issue, pull requests welcome. Just saying.
All right. Excellent. All right, well, that wraps up
All right.
our day. Thank you so much.
Thank you so much for hosting. Big round of applause for our MC.